What's up, YouTube? I'm here to explain the derivation for Kepler's first law. So before I continue, I just want to say that this is the law that describes the path that the planet takes. So if you can see in this diagram here, Kepler's law says that all planets travel in an elliptical orbit around their star. So we're going to define these objects in the elliptical orbit in terms of variables. So we have big M over here being the star. You can imagine that being the sun. We have little m being the mass of the Earth. We have r being the distance between the sun and the Earth, and d theta. So theta is just the angle that the mass is at with respect to this axis, the axis point here where it's at its minimum, where its distance is at the minimum. And d theta is just the small incremental changes of theta. Remember that this is just the change in the angle or whatever variable you're talking about as the limit approaches 0. And that this is where derivatives comes from. But to understand this, you need to have basic knowledge of calculus. So we'll go into the actual derivation right now. So this is the full derivation. We're not going to assume anything. This is the full derivation with all the calculus and second order differential equations involved. So we're going to start off with the formulas that we know of for rotating masses around the star. First, there's a gravitational force being acted upon this mass by the star, and that is given by Fg equals ma, which equals negative big G, big M, little m over r squared, where G is the constant, the gravitational constant, and big M is the star's mass, little m is the Earth's mass. So what we notice here right away is that these little m's can cancel out, which will be useful. By the way, it's negative because the force is acting in this direction. So, and you'll see later why having it negative first just makes everything a lot simpler. The other thing here is the equation for angular momentum, which is L, the angular momentum, equals I omega. So we know that I for a point mass, which we can treat it as such because it's acting on this mass from a very far distance, and it's rotating a long distance. You know, you can just treat it as a point mass. The mass does changes in mass within it don't really matter outside of it. So we can give I being the rotational mass by mr squared, and then we multiply this by omega. But I'm going to substitute omega for d theta over dt, and you'll see why. Now, another thing I'm going to do is I'm going to substitute r squared. So this is going to be something that we apply for everything just to make all of our calculations simpler. We're going to let r, and I'm going to write it up here so we all remember, equal the 1 over u. So therefore, I'm going to replace r squared, 1 over r squared, since it's in the denominator, by u squared. So we're going to end up getting this to be big G times big M times u squared. Now, over here, we have r squared in the numerator, so we can let this equal m d theta dt over u squared. Now, why this is useful is because we want to solve for d theta dt, because we're going to be substituting this in a lot, as you will see. So this is u squared, and we end up with d theta, and remember now that we only, L is a constant, since angular momentum is conserved without any external forces acting on it. So angular momentum is conserved, so L is going to be a constant. So we end up with L u squared over m. Remember, because you multiply the u squared on both sides, and then you divide the m on both sides, so we can isolate the d theta over dt. Now that we have this, we're going to be substituting this in a lot, and you'll see how. Now, we have this acceleration here. Now, there are two parts to the acceleration. There's the angular acceleration and the linear acceleration. So we can substitute a for those components, and we end up with that since the m's cancel out, we just have the acceleration. The second derivative of r with respect to dt squared. Now this is because, remember, this is basically the simplest form of writing acceleration in terms of calculus, really, that the first derivative of the position is going to be your velocity, and the derivative of velocity is equal to your derivative of your velocity is equal to your acceleration. My bad, I scratched out what I said earlier. The second part is the centripetal acceleration. So you have r omega squared. So we end up with this. So r omega squared I'll substitute omega for d theta over dt, since now this is the same thing as before. Your position in terms of angular movement, theta, the derivative of that is your angular velocity, which is omega, so that's d theta over dt. Now, let's move on to solving this part over here. Now, we know that r is equal to 1 over u, so what this is, since it's the second derivative, we have the derivative with respect to time of the first derivative, which is dr over dt. Now, I'm going to substitute r for 1 over u dt. Now, this derivative should be simple. We have some variable u, so we can take the derivative of that, which is negative 1 over u squared. Remember your power rule. You multiply the negative 1 and then reduce it by 1, so you have negative 1 over u, which is negative u to the negative 2. So we have 1 over u squared, the negative of that. Now, you have to apply your chain rule here, since this is with respect to time, not u. So we multiply this by du over dt. Now, we're going to apply the chain rule again. So this is where our equation that we derived here, d theta over dt, becomes useful, because the chain rule says that when we have a derivative, we can multiply the derivative with respect to another variable so that they kind of cancel out, as you'll see here. So I'll show you when it's written down. It makes more sense. So we have negative 1 over u squared, du over d theta. Now, when we have du over d theta, you can think of this just like fractions, right? Let's say you have this being 1. This will be 1 over 2. And then you multiply that by d theta over dt. So you have, let's say, remember, if we think of this as fractions, this is 2. And now let's think of dt as 1. So in terms of just like algebraic math, these would cancel out. But the reason why this is better is because we can substitute d theta dt for what we derived here. And what we'll end up with is we have negative 1 over u squared times lu squared over m. So the u squareds cancel out, and we end up with negative L over m du over d theta. Now, you're going to see why it's useful to have everything with respect to theta later, because we actually have some knowledge about how this planet will move with respect to theta, and that will be very useful for us to use. Now, I'm going to leave what we had up on top in the box over here, and this r equals 1 over u, so that you guys have that as a reference. Now, I'm going to continue on here. I'm going to leave this down here as well, and I'll rewrite the force equation later. But we want to find the second derivative now. So what we have here is the second derivative. So we want to take the derivative of this. So we have d over d theta, or the derivative with respect to time of a negative L over m. Now remember that L is a constant, so we can factor the L and the m out. So we can just take the derivative of du over d theta with respect to time. Now, your chain rule will be applied here as well. So as you will see, since we're taking the derivative with respect to theta, we're going to have to multiply the derivative of this, which is, by the way, just the second derivative of du over d theta. So we have d2u over d theta squared, multiplied by d theta over dt, since we want it with respect to t. And since you notice here again, because of the chain rule, what we have is we can substitute d theta over dt again. And we get that this is equal to negative L squared, since we're multiplying L and over m, u squared over m squared. Sorry that my handwriting is getting pretty messy. I'm trying to speed it up a little bit. So we have this multiplied by the second derivative of u with respect to d theta squared. Alright. Now that we have this expression over here, we can substitute everything back into our force equation. So let's get that force equation back over here. So remember that this is just the first part of, and by the way, since you guys are watching this as a video, you guys can skip forward through the parts that I'm kind of getting slow through. So we have the force, now the gravitational force is equal to negative g, big G for the gravitational constant, big M since the little m's cancel out, and then u squared, since we substituted r, the r in the denominator for u. And now this is equal to our total, the second derivative of r with respect to dt squared. We substitute that for u, so we have 1 over u. So we have L squared, u squared over m squared, which is what we got before, multiplied by the second derivative of u with respect to d theta squared. So this doesn't seem really helpful right now because, we started off with a second order differential in our first equation, and now we have another one in the second equation. But the thing is that this is respect to d theta, and we have some knowledge about that, so we can actually solve this when we have a second order differential equation. Now this is, now remember the second part to it, which we had r, so we're going to substitute r for 1 over u, omega squared, and remember that omega squared is d theta squared, and we actually have an equation for that, so let's square this over here, and we end up with L squared u to the fourth, since u squared is u to the fourth, times m squared. Now we notice that we have a lot of things to cancel out. We have first the u over here, and this becomes a 3. And then we have u squareds in all the terms. So we get rid of that, we get rid of that, and this becomes now a 1. And the negatives will cancel out, so we end up with that, and that all becoming kind of positive. So we can simplify this a little bit more. What we have now is gm is equal to, we have L squared over m squared. And now I'm just going to speed this up a little bit. We have an L squared over m squared in both terms, so we can just factor that out. Multiplied by the second derivative of u with respect to d theta squared, plus u. Since in this term, since we factored out the L squared over m squared, we have this plus u. Now this is going to take a familiar form. This is going to be a second order differential equation. So I'm going to rewrite it down here so that it's in a form that you probably would recognize. This is going to be really similar to what you did with if you're in AP Physics C, for example, you covered this with springs. This is a little bit beyond the scope of the AP Physics C course, but if you take like AT Physics, I know some schools offer that. That's something that you should cover. So that's the second order derivative. You also, in I think physics, any first year physics course in college, you should cover this. So you'd have the second order differential u with respect to d theta squared. Now we're going to multiply the m squared over L squared on both sides so that I kind of get all those constants on the other side. So we have plus u is equal to g big M little m squared over L squared. Now, how do we solve this? So second order differential equations can't really be solved per se, but what we can do is we know that this through trial and error, basically, that this will take the form of a cosine theta plus b sine theta. Now, to give an explanation for why that's true, I'll switch colors to green and kind of explain that on the side here before I erase it. So let's change that to a pencil. So we have green. Remember that what we have is we can bring this as a negative over here. By the way, as like kind of like a negative. And what you'll see here is that this generally means that the second order is equal to the negative of some variable. And so what we have here is the regular sine formula. So I'm going to use sine as an example. So remember that the second order differential is going to be the negative of whatever variable. So this is sine theta. What we have is the derivative of sine theta is cosine theta. Sorry, that was messed up, but you know what I mean. And then the derivative of cosine theta is negative sine theta. So these are the equations that satisfy this. And it's the same thing applied with cosine. What you have is positive cosine goes to negative sine, which the second derivative would then be negative cosine. So, now I'm going to show you how to solve the second order differential. I kind of erased the top there, but it doesn't matter. We don't really need this anymore up here, so that was just there for all the substitutions and stuff. So what we're going to have now is, I'm going to leave this equation down here and erase all that, so hopefully you copy that down or something. If any case, you can just not scroll back, go back through the video and kind of just see it for yourself. Now, let's go back to white, since that's like a regular chalk. So we're gonna get that, this general solution right now. And the reason why this is gonna be useful, since it's with respect to theta, is we can find a particular solution. So we're gonna have a cosine theta, plus b sine theta over here for our solution to the second order differential, plus b cosine theta. Now, I'm going to leave the rest of the equation here, but I'll focus particularly on the this general solution of a cosine theta plus or b sine theta. I'm going to change that right now because for some reason I put cosine theta twice. That's not going to work out very well, since the cosine thetas will probably just cancel out, and then that won't be very nice. So let's fix that right now. So this should be sine, not cosine. Since, as you can see, when you take the derivative of both of those solutions would satisfy the second order differential. Now, we have some knowledge about this ellipse. We have, this is moving up, and this is at a minimum. R is at a minimum over here when theta is equal to 0. So, I'm just going to put this in a box down here so we know that this is the general equation. That line got messed up. And we have now in red, we'll do it in red, or pink maybe. So now that theta is equal to 0, r is at a minimum, but remember that r over here is 1 over u. And since it's the inverse of that, we know that u is going to be at a maximum. And so what we know of that is that when u is at a maximum, the derivative is going to be, I'll show it over here, just so you, just to review basic knowledge of derivatives. When u is at a maximum, right, we can imagine that, in the most basic solution as a parabola, u is at a maximum over here. Now the derivative will be, I'm going to make that yellow, it's going to go through a 0, since, put it this way, the derivative shows that it's positive, therefore it's increasing, the negative is decreasing, so we know that at the maximum it has to equal 0. Now, the second derivative is just the slope of the first derivative, and it's a negative slope, so we know that the second derivative is negative. So, let's go ahead and write that out. So we know that d theta, or du with respect to d theta, which is the derivative of this, is equal to the derivative of this, so we have negative a sine theta plus b cosine theta, and this is equal to 0 when theta is equal to 0. So since we know what theta is, this is our particular case of theta, we can substitute theta. So we're gonna have, again, sorry for the sloppy handwriting, is equal to 0. Now we have that, we know that theta is equal to 0, so this is just going to become 0. Alright, because theta is equal to 0. Now, since this is 0, this entire thing should be 0. but cosine of 0 is 1, so we know that b is equal to 0. Now that we know that b is equal to 0, this makes the rest of it a little bit simpler. Since we know that b is equal to 0, honestly, this term will just go away. So we have d2u over d theta squared being the second derivative has to be negative. So now we're going to take the derivative of the entire thing. So I'm going to still include this, but it'll go away later. We have now the derivative of sine theta is just cosine theta, so we have negative a cosine theta. And then the derivative of cosine theta is negative sine theta, so we have minus b sine theta. Did I misspeak earlier? The derivative of cosine is negative sine theta. I'm not sure if I said that correctly, and we know that this needs to be negative, or we can say that it is less than 0. So we know that b is 0, and since this is at theta equals 0, sine theta is also 0. So cool, we have both of our zeros in the same place. We know that cosine of 0 is 1, so we have that negative a is less than 0. And now we can multiply the negative on both sides. And remember your rules for inequalities. A must then be greater than 0. And this makes sense, right? Because let's say a is 5. Negative 5 is less than 0, but 5 is greater than 0. So this is just basic knowledge of inequalities. But remember now that I got rid of the cosine theta by substituting 0 is just 1. 1 times anything is just whatever that anything is. So now that we have this knowledge, b will go away, and we end up with our particular solution, negative a cosine theta. Now remember that I meant to change the colors, but whatever. So now we have this particular solution for this case. A will be dependent on the specifics of this orbit, and when we solved it out, we end up realizing that a times, I believe, L squared over M squared, it doesn't matter, is the eccentricity of the orbit, but because it's an ellipse. So I'll go over that now that we get into actually proving that this is an ellipse. It's kind of crazy that it requires this much work, really, with the hard calculus proof to show that this is the equation for an ellipse. Anyway, so let's erase all of this so that we can substitute negative a cosine theta back into our equation, because now that we know that the particular solution of the second order derivative is negative a cosine theta, we have negative a cosine theta, and I'm going to set this equal to u, and you'll see why in a second. So we have negative a cosine theta, where a is a positive, plus, because remember I just subtracted this on both sides. Hopefully that makes sense. It's just basic algebra, really. Big G, big M times little m squared over L squared. And now, remember that u is 1 over r, or r is equal to 1 over u. So I want to find the reciprocal of this just to make it simpler. I'm going to combine them. So we have negative a L squared cosine theta plus g big M little m squared over L squared. So let me just finish writing that out. Alright, so we have that all over L squared. Anyway, now that that's the case, what we have now is that we can just find the reciprocal, and we have that r is equal to L squared, this big L squared at the top, all over. And now I'm going to switch this, and you'll see why, because if you realize this is taking a pretty familiar form. This is the familiar form of the polar form of the ellipse. And all we need to prove is that it is in the familiar form. So we have AL squared cosine of theta. Now, what we can do here to get it into its actual final form is we're going to divide the top and the bottom all these terms by gm, big M, little m, or we're gonna divide the top and the bottom by that. Yeah. So I'll show you right now. So what we have here is, I'll explain it. So we divide both top and bottom by gm little m squared, and what we get, I'll make this blue. So what we get here is that this will become 1 since we divided out. And remember, since we're dividing both sides, we can split this up into two fractions. So we have that this divided by gmm squared is 1. This divided by that, we're going to get a times L squared over gmm squared, cosine theta. And this also becomes L squared over g big M little m squared. And so we get that R, and it's good to write it in this way, in terms of theta, is equal to the quantity of L squared over gm big M little m squared. Is that hard to see? I should probably write it in I think it's hard to see. I'm going to rewrite this. Right. So we get that, I'll write it in red since I believe it might be easier to see. Alright, that's definitely better. Blue is too, mixed in too much with the board. So we have that R in terms of theta, and this is R in terms of theta, not R times theta, just to be clear about that. And we end up with the quantity of L squared divided by g big M little m squared, all over, now remember that since we're dividing these two different terms, we have 1 minus a, which depends on, actually a might just be alone the eccentricity if we think about it, a L squared over gm big M little m squared, cosine theta. And you can realize right there that this is the general form of an ellipse, and that is the derivation for Kepler's first law. If we want to, and this will be the last part, we can substitute this L squared over gmm squared, since they're all constants, by the constant k, and we end up with just the general form of an ellipse, which is k over 1 minus a k cosine theta. And I'm not really great with polar anything, so if you guys want to take the extra steps and see if you can look for the exact eccentricity, that's not necessary for the derivation of Kepler's first law, but this is what you need to know for the derivation of Kepler's first law, and that's what the point of this video was. So I hope you enjoyed it. Thank you for watching.